Welcome to Maths Chat Live, and this is another Saturday afternoon. So we are streaming on Twitter, Facebook, and YouTube. So this is a live interactive experience. We'd love you to get involved. So if you have any questions or thoughts, do post them in whichever social media channel you're on. It pops up on my little thing there, and when the time's right, I can get you involved in the conversation as well. So this is not just us, it's about you. This is what makes this thing really interactive. So today, very glad to have our next guest. It's something I've had on my mind for quite some time, is that it is maths, but maths is such a wide, all-encompassing subject when we talk about maths or mathematics, and it goes across through so many subjects really. I mean, I love the history of maths, for example, but in a sort of yin and yang way, which we were talking about earlier, maths and science are very interconnected. So and there's a few teachers and tutors I meet who teach both, and I'm very excited with our next guest, who has got some incredible experiments. A very practical man. He's primarily a physicist, I believe, but very much into his cosmology and maths as well. So I've cheesily called this one the maths in science and the science in maths. So a big welcome to David Boyce.
Hi, thank you for having me.
Yeah, it would be great to just if you let the viewers know what you do, what subjects you teach, at what level, just so they get an idea.
Right, so at the moment I teach all physics. I do a little tiny bit of biology at the moment, but in the past I've done chemistry, biology, maths, and physics at various different schools. But here it's nearly pure physics, so all the way up to A-level, and then all the way down to year 9. So everything encompassed in between.
Brilliant. Yes, physics. Well, we were wondering what we can talk about, and one of the first things that came out immediately is for maths, the maths in physics and physics in maths. Well, last week we had a little maths chat live. We were talking about manipulatives, and I mentioned like in learning maths, when you have concrete things, students learn better because they can apply it to reality, the real world we live in, and then once you learn those ideas, you abstract them out, and you can apply it to abstract ideas like space and time, and I came up with this. I thought of it, and when we think of Newton, the first thing people think of is his story with the apple, which is a very concrete image, isn't it? That's almost tied with his identity. It's like the apple falling and him having this eureka moment. And then he came up with the laws of gravity around fields and forces, and that idea was built upon by Einstein, and now think of it as like a space-time continuum being warped, distorted by masses. So it's like it all started from that concrete idea, isn't it? So it's the thing like students need to experience first, hands-on actually, and you're very good at doing that. So maybe you can just sort of give some examples of actual experiments on a kind of Newtonian ideas that are useful. Yeah.
All right. Well, where I work at the moment is Uppingham School, and we're only about 20 miles away from Woollersthorpe Manor, which is Isaac Newton's birthplace. And so several times over the past few years, I've popped down there and I've had a look at all of the displays. You get to have a look around his garden, and the apple tree is still there. The one that he spoke to his biographer about and wrote down the story that he was inspired to think about his law of universal gravitation by the sight of an apple falling down, and the realization that it was the same thing pulling it down as that kept the moon in orbit around the Earth. And I always find it amazing that what pupils think that Isaac Newton discovered. I mean, the very first thing that they think of is that he invented gravity. Like beforehand, everyone might be floating around. No, it's not quite right. Neither did he discover that things fall down, because kind of obviously things fall down. And Galileo was thinking of things falling down, and Aristotle was thinking of things falling down. Newton's real thing was linking and being able to explain the motion of the moon and space, and linking it to that same tangible thing that was within his experience. And so really what he was doing, he found a mathematical law that described not only those things that were kind of out there and up in space, but also it could explain the things that he saw in his garden, in his environment, in his surroundings. And I think for a physicist, our job is to demonstrate how the things within our experience can be explained with these mathematical laws. And I've got here Newton's Principia, which I'm working through at the moment. And the most interesting thing about it is what it's actually called. The actual name of the Principia. Let me get to the first page. Hang on, I'm trying to find it. Here we go. It's called The Mathematical Principles of Natural Philosophy.
Wow.
That is its full name. Principia comes from the Latin for principles, but basically it's the maths behind what we experience. And so this was the sort of foundation book of physics. There was things that we would now classify as physics that occurred before, especially Galileo and Archimedes and various people. An awful lot of astronomy and mathematics, especially in the Middle East. It's about 1,000 years ago. But the very first time that the actual discipline of physics came about, the idea that it's not just experiments, as Galileo had put forward, that can tell us about the universe. It's also by looking at mathematics. It created this whole new branch of physics. And the core part of it, if we in our physics teaching, we think about the looking at Galileo and how Galileo, his whole idea base was that you shouldn't believe it unless it can be proven. And that it could be proven in Galileo's mind experimentally. And so he created the scientific method. And when he died, it was about the same time that Newton was born. And Newton realized that there was almost like a secondary way that things could be proved in science. It doesn't necessarily have to be proven by experiment. It could be proven by logic. You could get an equation and you could do some mathematical process on it and get a different equation. You would still expect experimental procedure to match what that experiment was doing. But it was almost a case of finding the equation and then seeing whether or not the observed realities actually fit it. And so it was a completely different approach. It was almost like a maths first, observation second approach, whereas Galileo was very much observation first and maths second. So it creates these two different almost directions of looking at how physics and maths can work together. I mean, going back to your original point, you mentioned how these concrete examples that you can use and how Newton saw the apple falling was a concrete example. Here's a really interesting thing. If you think about A-level maths teaching and A-level physics teaching, in physics, we use the maths as a tool for explaining the observed phenomena that is familiar to us. And in mathematics, what we quite often do is we borrow a real-world example as a way of making the mathematics more readily understandable and relatable to our lives. So what you can see is that maths and physics, in their two different approaches, if physics goes experiment first, maths second, then it's very much following the Galileo's direction with this. And if it goes maths first, physics second, then it could be suggested that that's more Newtonian. So, here's throw like a controversial statement out there. You could argue that Newton was a pure mathematician. He just so happened to invent physics along the way.
Yes, that's great. Yeah, I mean he along with Leibniz is the calculus man, really, isn't he? So he came up with these so many incredible ideas. Lots in there. Yeah, Galileo did those experiments with the balls falling down to determine, I mean, this is a difficult idea, that everything falls at the same rate, or even that there is an acceleration at all, because it's really difficult to observe. And through his experiments, he proved through using, I mean, there's no stopwatches and things like that at that time, right? So they used some kind of water filling thing, if I remember seeing that documentary by Mr. Khalili, Professor Khalili even. So that's a great way of looking at the physics and the mechanics in A-level maths, where I use physics as an example, and the Yeah, the maths in the physics, where the maths is the tool. Yeah. There's this funny meme, I don't know if you've seen, where there's like Mr. Bean's looking at Coulomb's law, or is he looking at Newton's gravitational law, and then he's asked to do Coulomb's law, and he just looks like he derives Coulomb's law from the gravitational law, and that's a classic case of generalization of field theories. And then you have the fields, and then the theory works in the same way, and then it's just applied to a different type of field.
One of the most amazing things, and this is following the mathematics, is if you take Coulomb's law and you understand that it tells you about the force between two charged particles at a certain distance. It tells you all about, you can use it to derive other expressions for things like the strength of the electric field that is present, that is producing this force that this other charge is feeling. But when you look forward from that point, where does it go? Well, using some really complicated mathematics, James Clerk Maxwell put together something known as Maxwell's equations, and within it, it linked three things together in a really beautiful way. It linked this thing that we know as electric fields, this other thing that we know of as magnetic fields, and the distinction between the two as to actually what is it is really subtle, and you have to get all the way to Maxwell's equations, which are like second or third year undergraduate sort of level physics, before you have an appreciation for how are they different. But by linking them together, there was, well, if I was doing this, it would almost certainly be unexpected to me. I'm not sure whether or not Maxwell knew that this was going to pop out. But what he found by writing those three equations was he was then able to account for something that was really readily observed that doesn't obviously seem to be the product of these two things. Light. Electromagnetic radiation was first understood in terms of its oscillation in electric and magnetic fields through the Maxwell's equations. Now, because of the similarity between Coulomb's law and Newton's law of gravitation, they're almost exactly the same, and you can go through and you can work out a field strength and it looks exactly the same. And though there are some differences in that charges can be positive and negative, and with mass you only get positive mass, the actual construct of the mathematics, the shape of the equations, is almost exactly the same. So the test is, can you follow the line of derivation that Maxwell used to produce his Maxwell's equations that describe these waves of electromagnetic radiation? Can you do that to gravity? And so a couple of years ago, I had a look and I thought, well, if I just follow the derivation for Maxwell's equations, but start not with Coulomb's law, but start with Newton's law of gravitation, I would end up with like a set of things, a set of formula that would be like the gravity equivalent of Maxwell's equations. And you can actually do this, and you produce these four formula, which are called the electrogravity equations, and they predict the existence of gravitational waves, which is something that we have now detected. And it is an incredible thing, because right through the 1960s and 70s, we were believing that gravity was perhaps mediated by some really tiny particle, the graviton, because we see within the standard model of physics that we can explain the interaction of lots of things through it's either a photon carrying no mass or a W or Z boson, and this explains to us how certain forces let other objects at a distance know that they're there, for example. So how do we know that this charge has moved? It's because it sent in a photon to tell the universe about its movement. How do we know that this particle has decayed into something else? It might be that it's sent away a W or a Z boson. How do we know about what is the force mediating particle for the strong nuclear force? Well, that's the gluon. What about gravity? And everyone thought that because of this thing, that they all were described as particles, maybe gravity was a particle too. But then, of course, we've now detected gravitational waves, that supernova and black holes merging and all sorts of things in the very distant universe are actually rippling the fabric of space and time. And we detect those ripples, distorting our laser interferometers. And what is really curious about that is that it interacts with us in a wave nature. Whereas if you think about what quantum mechanics told us, is that when things were traveling through space, they would, unobserved, they would almost certainly, whether or not it was light or matter, it would travel unobserved as a wave. And then only when it interacted with matter would it then become a particle. And the fact that gravity does not do this, it interacts as a wave all the time. And there's no experiment has been designed so far that has yet to show that gravity can act like a particle. It means that gravity is fundamentally different from everything else that we see in nature. And one of the most exciting things about physics, for me, is that we just don't know. That the further you go through something, you reach this, I don't know whether or not to describe it as unsatisfactory ending, because we get to a point where the final end is we don't know. And you might find that either really frustrating because you want to know, or actually that might be the thing that is so interesting about it in the first place. So Newton stood in his garden watching an apple fall. Did he realize just the massive can of worms that he was opening, and the complications that come with gravity? His famous saying, "If I've seen further than others, it's because I've stood on the shoulders of giants." And some people suggest that that's a taunt at one of his rivals. But actually, Newton was a very well-read man. He had a massive library and he was extremely studious. And he spent hours, all night long sometimes, reading, learning, developing, pushing, and coming up with new things. And I think that where we are now, we are seeing exceptionally far because we're standing on the shoulders of Newton himself.
Wow, that's pretty profound. Yeah, I mean, started from that observation, and the plot just gets thickens and thickens and thickens, and this is a state we like as being scientists and mathematicians. I certainly do. That it's not resolved, which means there is still thought to be done. There's still things to be found out. There's still experiments to be done. There's still equations to be mulled over. Brilliant, yeah, and bringing it to teaching, you mentioned Newton there with Hooke, presumably, so we can kind of tie it in very nicely with this idea of, I saw a tweet from a maths teacher about looking for examples of proportionality in physics, right? So that's Hooke's law for direct proportion and all the Newtonian mechanics stuff as well. How would you link that? For I know in maths they don't do that enough, where you use the proportional symbol and then change it to a constant and then do an experiment, find the constant of proportionality. It's only once you do it enough times. Certainly I remember in my journey, I ended up doing mechanical engineering because I was just a mechanics nut, so like my sort of planes and cars and trains, but for me personally, I had to actually just see those pulleys, understand what friction is by actually doing the experiments, doing the measurements. How do you find that, or maybe you have examples of experiments you do for proportionality?
In terms of proportionality, so you mentioned Hooke's law. That's a really good one for something being directly proportional to something else. The whole basis of what proportionality means, though, that's something that can be really fundamentally described. If you take it back to the simplest ratio of quantities that they might know, distance divided by time will give you speed. These two things are proportional when you're traveling at constant speed. If you cover a certain amount of meters and a certain amount of seconds, then if your speed hasn't changed and you go, twice as many seconds, you will have gone twice as far as you had in the first time interval. So at a really fundamental basis, all of our equations that involve just three variables are just, they are like experiments in proportionality. One of the things that we do in physics is we try as much as possible to say, hey, look at this happening here. Look at this phenomenon. Isn't this interesting? You've seen this before. This is within your life experiences. You've seen this every time you looked in a mirror or something like that. But how is it actually working? And at some point, we go from describing the physics that's going on to describing it quantitatively so that we could put numbers into formulas and we could make predictions about what would happen if we put 3 times as much mass on this trolley. We can make predictions because we can represent it with formula. And then we hammer into them that it's formulas, formulas, formulas. And you've got to learn all these equations and, you've got to apply all these things. And then you get to sometime in probably the end of year 12. And I think the very first time that it really happens is when you start then playing with gravity. The gravitational field strength on a planet. Now, you would know that the gravitational field strength was equal to G-mm over r squared, or some equation that would help you to do it. No, actually, I told you too many m's there. You've got to cancel one of those m's out. You get the picture. There's an equation that represents that quantity that you're trying to find. But then they throw in a question like this, and they'll say, what if... for example, if we were to, let's look at Kepler's laws, for example, the speed at which something would go around the sun, its time period squared is proportional to the distance cubed multiplied by some great big constant that you don't know. And what they might do is give you the information for, say, Venus, and you'd be able, from that, to work out the constant of proportionality. And given that constant proportionality only depends on something like the gravitational constant and the mass of the sun, it would be the same constant for a different planet. And you have to do this thing where it feels really kind of alien. You've gone from being trained that you get the equation, you put the numbers into it, and you get the answer out. Here, you're not given all of the numbers. And suddenly you have to make this jump and realize about proportionality, that the relationship between, for example, the force of gravity and the distance, you could work out a constant of proportionality that links those two. And if the situation was changed so that everything else that was represented by the proportionality constant was going to stay the same, then you don't actually need any of the other numbers for the formula. And so it means that all of the formula that we've encountered can be treated as proportionalities. We can replace the things in the equations that we don't know by constants and just have something equals that constant multiplied by this other thing, simplistically. And we do that in the gravity section. We quite often, we would say something like, what would the gravitational field strength be like on a planet that was twice as dense and 3 times the radius? And you would solve that, not because you haven't been told what the mass of the planet is, and you've not been told any of these things, but what you do know is that it's going to be proportional. The proportionality can be found from the equation, which means that you can work it out. So proportionality in physics is something that it's right there at the beginning, in the earliest days of distance over time. But actually, it comes back in to be a really powerful tool later on, when you first realize that you don't need all of the numbers in the equations to still work things out.
Yeah, no, fantastic. It's proportional reasoning in maths. Really, it's like it's multiplicative proportional reasoning, and it's such a core idea, isn't it? It's if you know what the proportional relationship is, and maths, it comes up all the time with even in the very early stages. I was doing area scale factors with a tutee yesterday, in fact, and so this is a very common one. They didn't understand why the area scales so differently to the lengths, and for that you really do need to get some sketches out and actually analyze that this is a 2-dimensional situation, and in one dimension this, one dimension that. It's the same with volume scaling, and once to understand, this is the area scales up in this proportion, the volume scales up in this, the cube and square, and then they can kind of generalize, and they can do those type of questions with and without numbers right from that very early stage. And trigonometry is proportional for that given angle. That's that ratio between the perpendicular and the hypotenuse, or those two lengths. For a different angle, the ratio changes, but essentially it's similar triangles. Could call it proportionality.
Well, that leads me to thinking about something. If I could share my screen, I want to just draw on the screen. Is that possible? I want to just draw on my whiteboard for a second.
Yeah, sure. You can either screen share or yeah, I can see that.
Can you see my whiteboard now?
It's all completely white, yeah.
If I had a random area like this, and this area was in centimeters squared, one of the things that we quite often have to do in physics is go between things like centimeters squared and meters squared. If you're, for example, trying to work out the pressure of something, it's force divided by area, but it's only going to give you an answer in pascals or newtons per meter squared if you indeed put the answer in as meters squared for the area. And one of the things that most my students and students generally kind of struggle with is, how do I get this area in centimeters into this area in meters, into meters? And it's, as you said, that it doesn't scale. It's not just a case of there's a difference of 100 in these, because there's not. There's going to be a significantly different difference. And there's two ways. There's two ways that I could do this. The first way is I could give them a conversion factor. Oh, you just multiply it by so many thousand or whatever. And you're telling them, for this one example, here is the one thing that you need to remember to always do this process. And the second way is you could work it out. And with this one, for example, if I had the area in centimeters, I would take the area in centimeters squared. And what I would want to do is I would want to model it. Like if that was squashed into a physical square shape like this, just visualizing it, the same area, then it would have two side lengths, wouldn't it? Imagine if it was a square, they'd be equal to each other. And I'd be able to find out what they were by square rooting it. And so this now is equal to L. I've found out what one of the side lengths of that visualized area would be. Now, from that point there, I know that that is its side length in centimeters. Now, I can convert centimeters into meters by dividing by 100. So if I then divide this answer by 100, I've worked out what the side lengths are in meters. All I then have to do is square it to get my answer back as a meter squared. And so what I've done is I've taught them how to work it out. And you can go between millimeters, millimeters squared, divided square root, divide by 1,000 this time, and all squared will get millimeters into meters squared. Or alternatively, you can put a volume in centimeters cubed in there and then go, it's exactly the same, but instead we, oops, do you know what? I went wrong. I'm going to just draw it somewhere else. The volume in centimeters cubed divided by 100, and its cube root there, instead of, and this will basically give it in meters cubed. And you can see that you can work out any area in millimeters squared or centimeters squared, or any volume in centimeters cubed or millimeters cubed, and you can convert it into meters squared or meters cubed. What I've done here is the second option is conceptual teaching. I've given you the tools to work it out in future, whereas the first one is an example of procedural teaching. So the first one, what I've done there is I've told you how to do it, and you can do it, but you can't use that technique. You can't modify it, you can't synthesize it. It works in only this one situation. And to a certain extent, this can be described as teaching to the exam. What it means is you can answer the exam questions, but you don't know what you're doing. You don't know what this technique actually is doing to the numbers. So you can get the right answer, but you don't understand what it is that you've actually done. And this leads to, I want to clear all of this, this leads to a really contentious thing in physics teaching, and also in other subjects like chemistry, biology, and also in maths, is the use of the formula triangle. The formula triangle, for example, wave speed, v, f, lambda, whatever, it means that it helps me to rearrange these variables, because if I was to have the wave speed was equal to the frequency times the wavelength as a tool for teaching this. Obviously, I can represent it in symbols, and the symbols there. I'm sure all of your viewers will be familiar with this, but you cover up the one that you're making subject to the equation. So I try and find lambda, cover that up, and I can see that v over f is how to rearrange that to find lambda, or I could do f is v over lambda, and that v is f lambda. And so I can work out all three of the possibilities from this triangle. Really useful, eh? Well, we did some research on this, and we found that this was actually invented by Fleming, who did the Fleming's left-hand rules of induction and whatever. And he obviously was always thinking about how he could demonstrate things tactilely with his hands, and he came up with this. And now this is the favorite mechanism for teaching people how to rearrange for CGP revision guides. And so you see, first page normally, you need to know how to use triangles because we're going to provide this procedure. And if you encounter any different quantities, you then need to be able to apply it to lots of different situations. Great, eh? And I'm sure that out there are thousands of people that can honestly say that they passed their GCSEs because of the formula triangle. I mean, I remember using the formula triangle myself. It is a nice method, but there's a problem. And the problem comes from this. Acceleration, for example, is the change in velocity. And if we call the initial velocity u and the final velocity v, and the change in velocity is going to be v minus u over a change in time. So we could just represent that as t, but we actually mean delta t. But fine, here is a formula. Notice straight away, if I try to put that into the formula triangle, then what is at the top is v minus u over a and t. And straight away, this has become a situation where it doesn't work. You could say that, yeah, v minus u is equal to at. I could get that. I could say that v minus u divided by a is t. I can get that from the triangle, and I can do v minus u over t would give a, but the triangle does not show me how to get v, and the triangle does not show me how to get u. I've got no method. I've got no way of doing it. And then straight away, we can go with Torricelli's equation, v squared equals u squared plus 2as. How do I stick that into a triangle? How do I stick f equals minus gmm over r squared? They don't go into a triangle. But this is the thing. At GCSE, you handle exclusively situations that are at most, well, probably you'd not be called to rearrange something like this. You'd probably be called to rearrange something like this, and nothing more difficult. Though this is in the GCSE, and so is this, you're more likely to just have to put them into the formula before rearranging. The things like this, though, these are A-level standard, and you need to have a method that actually works for rearranging this. You need to understand what the triangle is doing, what the rearrangement is. And this takes us straight back to algebra. And this is what is being forgotten, is that the skill of rearranging is just basic algebra. And we're making it confusing by giving words and meanings to these symbols. When it was A equals B over C, it was straightforward. Most of your pupils knew how to rearrange it because the cognitive load was reduced to the point where everything was just represented by symbols. What I've been working on at the moment is seeing whether or not is it more effective to stop and spend 10 minutes teaching algebra, or at least reteaching the algebra, reminding them of the algebra, than it is to teach them the triangle method. And you know, you lose the 10 minutes, this takes longer, but ultimately what you give them is an understanding. And whether or not they then use the triangle method, they actually understand what the triangle is doing as well as this. So the triangle itself is an example of procedural teaching, whereas algebra is an example of conceptual teaching. So you'd think that the argument is that we should always favor conceptual teaching over procedural teaching. It's worthwhile to make sure that everyone knows exactly what the method is that they're using while they're using it. But here's an interesting thing. This is a reflection on the whole debate by a maths teacher. And that was on SOHCAHTOA. So the relationship between the angles and sides of right-angled triangles is found through the trigonometric functions sine, cos, and tan. And he points out that when sine, cos, and tan are introduced to pupils, normally there'd be a lesson where sine and cos are seen in relation to position on the edge of a circle, that they are, they're connected to a circle, and tan is the ratio of the two. He said, but very quickly they go past it. Very quickly, they almost need to just say, hey, this is a thing, and then they go past it, because from that moment onwards, you don't need to know. You don't really need to know what sine, cos, and tan are actually doing to your numbers, but to know that they are a function that makes this equal that, and that this is a function that you can use. And so some mathematicians that I've spoken to argue that if there are certain situations where understanding the method is not as important, at least in the early stages of learning, as being able to use the method with ignorance of what it's actually doing. So here we have the kind of the two-way interaction between maths and physics. With the physics, we're following the scientific method. And what I say to my pupils when they put bold answers down on their page is like, show me you're working. I say, this is a dialogue. I'm not interested in the answer. I want to see how it's proven. Prove to me. And I wish actually rather than say things like, what is the acceleration, that they should say, prove to me, prove to the examiner what the acceleration is. Because we're not interested in what the acceleration is. So we're interested in that the student can demonstrate it, and that the methodology is really clear that the student is using. Whereas the maths teacher argued the fact that in some situations, the methodology is not as important as applying a sort of standard method, like using SOHCAHTOA with triangles. So is it causing like a great chasm between maths and physics? No, I just think that it's just intrinsic to the slight differences between us that we stress the methodology in physics, whereas it's one of those places that in maths it might be slightly different. The importance of understanding how it's working sometimes is secondary to being able to make it work. So where are we? Well, we're kind of in a position where there is this slight difference. There's no great consensus over which is the right way to do things. But I actually think that, this is why physics and maths can complement each other, because there are always, there's a maths way of solving this problem and a physics approach, each with a slightly different stress on what is the important part of the work.
Well, I'm very glad you brought that one up, because that would have come up anyway. Yeah, definitely. I mean, SOHCAHTOA is essentially it is a formula triangle. I've seen some of my tutees show that in a formula triangle, and there is no. It's all context based, isn't it? It depends on which classroom, which particular students you have. In my case, which tutee, and it may be better to start off with the procedural to get the fluency. It's that what's that film in the Kung Fu guy where gets him to like scrub on the car. It says like, I'm just getting you used to that motion. Go scrub the car. It's like, why am I scrubbing the car? Well, that's because you get used to that motion. And that's I mean, learning is a very complex, I would say, even an iterative process. You look at it maybe from the procedural, then you understand a little bit of the conceptual, you go back to the procedural, get more fluent, then you go back to the conceptual from another angle, and that forever keeps happening. So as controversial as they are, it's all context dependent, and if for me someone is in halfway through year 11 and a formula triangle is what they need to get the mark and pass that exam for the formula triangle, yes. If I happen to be teaching them maths as well, I'll tell them actually the formula triangle is just your fractional, like exactly the way you put it. It's basically it's algebra, and we can only kind of get away with it in up to GCSE sciences because just the number of variables we're dealing with and the situations, as you showed even at GCSE with the acceleration equation and a whole bunch of other stuff, it just wouldn't work. And so yeah, it's all as long as you explain it to them, you ultimately you know who's in front of you and what's right for them. You certainly wouldn't be doing formula triangles at A level, because that's a stage where they do need to thoroughly understand proportionality in all its forms. Yeah, fantastic. We also had a chat about just looking at A level physics and A level maths, or maybe, yeah, what I see for my mechanics students in A level mechanics is they often need a recap of GCSE mechanics before they get into. So there's this bridging period, and they might not have seen some topics in lower sixth at all, and suddenly you get all of this kind of moment stuff popping up in the second year. So they've had a whole year without any moments, and the stuff they did in moments at GCSE was fairly rudimentary, or even the Newton's law stuff. So there's definitely this kind of bridging, and also understanding it in a more concrete form, because like, what is a frictionless pulley? I mean, what is a pulley? Even some people don't. I've had students who don't know what a pulley is, so you have to actually get a physical pulley out or show a pulley in a video. Yeah, perhaps you could take us through some of your ideas on how you bridge this process.
Well, I'm going to share my screen again. The bridging between GCSE and A level, I think it has to be quite significant. Now, I don't know if you can. It's going to see it maximized. Can you see it? Is it there?
Yeah, it's pretty good. Yeah.
Right.
It's full maximized. Yeah.
I've worked in a number of schools. They've all had different entry requirements on the A-level physics. But one thing that is nearly always true is that if you really struggle with maths, A-level physics is going to be very, very, very hard for you. A sound mathematical understanding is just part of the things that is necessary. And the jump between the level of mathematics that's present in GCSE physics and A-level physics is quite a large jump. And there are certain skills that we need almost from the get-go, that they will have been taught in GCSE, but I can hear feedback. Is that my end or your end?
There's probably some building works going on here.
Okay,
yeah.
That's fine. I just didn't want it to be my.
That's my end. Yeah, I'll mute while it's going here.
Okay. So making sure that they enter A-level ready to go mathematically is really important. And so one of the things that I created a few years ago, and I still use this, is in those first few lessons when we're looking at mechanics, and the actual mechanics is pretty similar to the mechanics that we were doing at GCSE, or at least they would have done in GCSE mathematics, is I put up a slide at the end and spend 10 minutes doing something like this, because these, for the year 12, these are the main skills that are going to be useful to them. Sockotella, rearranging logarithms, graph drawing, analysis of log plots, geometry, problem solving, calculus. Beneficial, it says, but not strictly necessary. But there are more simple skills as well, like grassroots skills, like putting numbers into a calculator. You think that, and so this would be something I'd put on the board, and I'd say, could you just make B the subject of all of these? Because this is just algebra, and they start off really straightforward and they get really hard towards the end. And I always like to see who in 10 minutes can solve them all, and there'll always be one bright spark that defies all. I'd still be working on about number 4, and they'd be like, I've done, sir. And I'm like, whoa, somebody very, very keen on their mathematics. But by showing them this in a physics lesson is really anchoring the physics that we're talking about in the mathematics that they should know. And of course, this goes to different layers. We basically are going to need all of the rearrangement for the first 2 columns, and the stuff on the right-hand side is beneficial, but it's not strictly necessary. And probably the second one down on the right-hand side is probably needed for things like Young's modulus and those sorts of things, where there's 4 variables. But just that rearrangement practice is really, really key. And I've heard of A-level pupils that are getting into their final year and they still can't rearrange the 3 variables. And that's a stop everything moment that why are you carrying on with other things if they can't do this? It almost needs, that's where the intervention needs to happen. You need to say, this is such a fundamental skill, we can't carry on until we've mastered this. But the actual whole thing, and we forget as teachers that this whole thing is kind of complex. We could sit there and talk about numerators and denominators and make the language really complicated. Or when we think about what is actually going on here, if we take it right back to the idea that you've got to do the same thing to both sides on the equal sign, that if we take, for example, the first one in the middle column there, do we square root first? Do we divide by c? How do we get that c on the other side? Do we times c to both sides? A pupil's going to look at that and it's not going to be quite clear. The two things that they need to remember is that undoing a multiply requires you to divide. If you divide both sides by c, the c on the right-hand side cancels out, and it's now a divided by c on the left. But how did I know to do that before handling the square? It's because intuitively, I'm following the reverse BIDMAS of that approach. I'm looking at B, which I'm trying to get by myself, and understanding that in the order in which those operators are acting, it's going to be squared first and then multiplied by C second, which means I've got to divide by C first and then square root it afterwards. That there is actually skills that, unless we physically talk about them, are not obvious. That when they get more complicated, they have to do it. They have to rearrange in the reverse BIDMAS order on the value that they're trying to get. Doing this gives you the opportunity to talk that through them. If you forgot, here's a reminder. If you never learned it in the first place, here is what it is. You need this next lesson. And what you could possibly do, if you think that somebody has forgotten, give them this again and say, this, you did this before, here it is again. And there are other things in A-level physics, like the representation of things like seconds squared as represented as like seconds to the -1, for example, or seconds to the -2. The representing them in index notation is something that we suddenly change between GCSE and A-level, and we just straight away we go from saying, well, meters / seconds goes to meters seconds to the -1, no explanation. And so that's that. And here's another great one: putting numbers into your calculator accurately, because people are terrible at it, and it's not a skill they just know how to do. Right? What we have here, this is an equation they don't really want to know. It's Einstein's mass energy equivalence law, but divided by the Lorentz contraction, the Lorentz factor even. So basically it's saying that the energy is going to be dependent on how close to the speed of light this object is traveling at. It doesn't matter, it's just an equation. And here's some big numbers, and these big numbers in standard form, are 9 times 10 to the -31. So what we do here is we say, okay, I want you to put these numbers in that formula and bring the answer up onto your calculator. And you would imagine that they would all get the same answer because it's straightforward. It's just numbers substituted into that. But in nearly every single year I've ever done this, almost always, every single calculator will have a different answer, because their precision of entering these numbers into the calculator will just completely go out of the window. Some of them will be using different methods. They'll be putting brackets in, and there's the student that is going mad with the brackets and putting like 30 brackets opening, and then, and that's great. And then you can talk to them how there's different ways of doing things. And my own preferred way is, so that I can make sure there was no BIDMAS error as a result of like faulty brackets, I tend to use the answer key a lot. I'd go m times c squared equals answer divided by brackets, and then break it into little sections like that. And it's how I do it. I think there's value in doing it that way, but it's so interesting that you have to actually address these skills. Say, okay, come on, put some numbers into a thing. Using constants is straightforward, and just an understanding that between the different types of physical quantity, how some of them are variables that can take any number, and how the formulas that link variables are basically just mathematical functions. This formula just basically changes this number on the range onto the domain. It takes your independent variable and produces the dependent variable, and talking about it in terms of what the different quantities represent. Before we even talk about scalars or vectors or anything like that, talk about the difference between a quantity that is just a variable in one of these equations and a quantity that is a constant in one of these equations, like the speed of light, for example, and how they're fundamentally different. That is something that is worth drawing to your attention. Showing you're working out, having a really good methodology and almost modeling what you want to see so that the pupils actually follow it. That we've got to remember all sorts of things. On the left-hand side, there's a slight typo, but it really does show what's going on inside a physicist's mind. It should say, remember, first of all, the first thing is the variables. And what I'd say to my pupils, even before the substitution stage, write down the numbers given in the question and put them equal to the quantity. So A equals minus 9.81 meters per second squared, and V equals this, that, and the other. And you can see which equation you need to use more. And on this thing on the left-hand side, I've accidentally put units first, because physics teachers are obsessed with units. It's the thing that everyone always forgets all the time. Now, there is a contentious point here, and some people would argue this is all wrong. But if you go look in a professional physics work, you will always see that the equation is displayed in symbol form. It's rearranged into the format, so it's subject to the thing you're trying to find, and then the substitution stage occurs. And you'll see that in the Feynman lectures, and you see it in 1,000 different examples. However, GCSE and A-level physics is being steered towards a different approach, which is to substitute the numbers into the equation first and then rearrange afterwards. In fact, there's marks for doing it that way round, and then the answer in the unit. But the key thing is that we take some GCSE level question and you model how you want them to do it. And you always say things like, this is a dialogue between you and the examiner. The examiner has the answer already. They're not interested in what the answer is. They're interested in whether or not you can find it and that you can show how you found it, and really make a stress on those sorts of points. A little bit of geometry, and then, of course, going on to graph drawing, which physicists stress all the time, because we're a great fan of graphs in physics. There's nothing that we won't graph, can't graph. But actually doing that bridging work and making it all about the mathematics is one of the most powerful uses of time in the early part of a physics course. Without the mathematics, they will not make the progress that you need them to make. It is the firm foundation you're going to build everything else on. And physics itself, I think the very first time you learn it, or you learn about it, they're like individual pieces of a jigsaw puzzle. And you could perhaps match it up to the box and go, well, I know that this is the top of the Eiffel Tower, and that this is the Arc de Triomphe. And then as you learn more of the physics, more of the context, you start to get it to go, you get more pieces. But the times when it really, really works for you is when those separated sections start to link together and you realize this is connected to that. And I'd argue that is actually what physics is. It's not the individual laws of physics, but it's the connections between them. Now, how does this fit with the whole you need to have the maths? Well, I don't know about you at all, but certainly if I'm doing a jigsaw, I always start with the edge. I go around the edge because you find all the pieces with the flat side. And from that point, it gives you like a reference frame. And you know that relative to that reference frame, the top of the Eiffel Tower is going to be just there. And that is what I think maths is in the physical sciences. It is the reference frame. It is the thing that you have to have there in place to be able to correctly position all of the knowledge and the structure and all of the skills, all of the techniques, everything that we do.
Fantastic. Yeah, loads in there. Yeah. I mean, Dee's just wrote on YouTube, I tell my students that the narrative is important, not just to show the examiner that you know what you're doing, but it also allows a student to follow their own train of thought. So you're producing a good mathematician. If it's a dialogue both between you and the examiner and with yourself to help clarify your own thoughts. That's a really good way of putting it, actually. I've never thought about putting it that way. And sure, you're working out is a problem we all face as teachers. It's like probably one of the biggest ones, both in maths and any subject, really. And yeah, the whole idea of that as well. It's so good that you do that. And would love to have those rearranging equations worksheet. It's a really good worksheet, that one, actually. That could be used easily at like a higher GCSE maths, for example. Just the idea that this is what the equal symbol really means. It means you can apply a function on this side of the equation and that side, and modify it, which like the inverse function of multiplication, which is a divide, and going back to what we call in maths like the field axioms. So you're just reversing the order, and but that skill set's got to be practiced and reinforced pretty much throughout the learning journey. Actually, it happens. I almost do it almost every year, like year 9, year 10, year 11. It just, you have to keep reinforcing the idea that that's what the equal signs mean. That's what rearranging means. That rearranging an equation is a skill set. And the units thing is absolutely vital in maths as well. I've known students who don't remember the formula for density, but the units of density is given in the answer already. So essentially they've given you the formula for working out the density, and you just look at the unit and the formula is there, so you just plug in the numbers and you get, there's so much you can get from dimensional analysis. Okay, well, I know that you have to finish up at 1. You are still at school. I can see that you've got a blackboard behind you with the Newton. So yeah, we'll start wrapping up. Are there any kind of last thoughts you'd like to share?
Not really. I think probably the only thing is that though the approach might be slightly different between physicists and mathematicians, it's the same ground over which we're walking. So I think working together is probably the best way of finding a way forward.
Yeah, I know that's a great vision. And how would you suggest that in sort of practical terms? Like how the science and maths people have a CPD session together, or how do you foster that kind of communication?
Yeah, and just get to know the teachers in the other departments. Find out and ask the pupils, what are you doing? What are you doing in maths at the moment? What are you learning in physics right now? So that you get a feel for where they're at, and you can ask them questions about how confident do they feel about this. How confident do you feel about calculus? Can you apply the chain rule yet? There's no point in me talking about it until perhaps it's already been introduced formally in mathematics. But just making sure that there's just that awareness of what the pupil might be doing over on the other side, and also what the teachers might be doing.
Fantastic. And that's one of my visions, is getting these chats going. That's probably the first stage, is just getting chats between colleagues going, between those who teach physics, those who teach maths, who teach primary maths, secondary maths, any type of maths, any type of science. I've still got loads of things I can ask you. You've got great experiments on YouTube, so we'll have to get you onto another science specific one or another maths one, so we can talk us through some of the incredible experiments you do, and I'll definitely plug to your YouTube channel in that Twitter. So yeah, once again, thanks so much for your time. And this recording so if you're watching the recording, do ask us questions. We are both on Twitter and on YouTube, and I think you're on LinkedIn as well. So if anything comes up for you while you're watching, do just reply to us, and we'll do our best to address it. So brilliant. We'll wrap up now. Just do a little wave bye, and then we can finish up there. So I'll just do that for